Okay, the recording starts. I cannot minimize. We will start a new chapter, chapter 5, your textbook. So we will talk about chapter 4 is about the operational amplifiers. We will talk about this semester. So let's skip chapter 4 right now. So chapter 5 is the additional circuit series that can further simplify the circuit. Let's take a look. So our goal is to make a complicated circuit to simplify that, obtain the equivalent circuit, so we can carry out the analysis. So this is a review of what we learned in previous chapters. For example, for the two resistors in series R1 and R2, the equivalent resistance equals R1 plus R2. This simplifies this. And for the two resistors in parallel, we can obtain the equivalent resistance. For the two voltage sources in series, we can get the equivalent with the equivalent voltage source. This will be on the exam. You need to know how to simplify the voltage source. So this is what we learned in chapter 2 in previous chapters. And also we learned this, two current sources in parallel, we can obtain the equivalent current source. And what we will learn in chapter 5.3, we will learn this. So for the voltage source and the current source, in the previous chapter, we discussed the ideal scenario. But in actual scenario, they have some resistance. So that these two circuits are equivalent. Later we will introduce it. This is called the source transformation. So that a voltage source that is parallel with the resistor can be equivalent. The equivalent can be converted to a current source in series with the resistor. So we will talk about this in chapter 5.3. So this is what we learned in the previous chapters. And what is the circuits we discussed in previous chapters are all linear circuits. And the linearity is a property of an element describing a linear relationship between cause and effect. The linearity requires both additivity and homogeneity. So let's take a look. So a system is called linear if it satisfies additivity and homogeneity. Let's take a look at additivity. So that the input, so f is our function, right? So if we have x1 as the input, we can get fx1. If we have x2 as the input, we have fx2. But if we put the sum of x1 and x2 into this function, if we get f1 plus fx1 plus fx2, so we call this additivity. An example is that, let's assume that this function is fx equals 3 times x. So for x1, we have 3x1. For x2, we have 3x2. If we put the sum of x1 and x2 as the input to the function, we can get 3 times x1 plus x2, which equals fx1 plus fx2, 3x1 plus. So fx is additive. But let's have another example that the fx is not additive. So let's have an example. For example, if x me see, if fx equals fx squared in this additive. So let's take a look. Fx1 equals x1 squared. Fx2 equals x2 squared. Right. What is fx1 plus fx2? It equals x1 plus x2 squared. Right. This equals x1 squared plus x2 squared plus 2 times x1 times x2. Right. That is equal fx1 plus fx2. That are they equal? They are not equal. So this is not linear. So this function is not linear. So all the linear function should satisfy this additive. And the homogeneous means that here it's also called scaling. That when we time, so if we times the input by 5, the output should also multiply by 5. So that's this characteristic. So fa times x. So the input times a, the output should also times a. So this is the homogeneous. So for a linear system, we should satisfy these two characteristics. The linearity, that is the additivity and the homogeneity condition, can be started by using a single equation. So that fx is linear if the input is a1 times x1 plus a2 times x2 equals a1 times fx1 plus a2 fx2. So fx equals 3x. So we use plugging this into the input and take a look at the output. If the output equals a1 times fx1 plus a2 times 2, we say fx. So how does this apply to circuit analysis? Let's use an example to illustrate this. So for this circuit, we are familiar with this circuit. In chapter 2, we discussed how to solve this circuit. That is, calculate the equivalent resistance, right? And then use the voltage division or current division to obtain the voltage and current on each element. But now we use another method to solve this circuit. Do you remember how to solve this circuit? This will also be taken back, but the method that discussed today will not be that. So for the same circuit, we can use different methods to solve it. So in previous chapter, we discussed the equivalent resistance, voltage, and current division to solve this circuit. And today we introduce another method. So how to solve this circuit is that, so this is a linear circuit. Okay. So we have the input. We want to calculate the output. Okay. So what we do is that we assume we do not know the value for output. We do not know the value for Vout, but we assume Vout. We assume Vout is 1 volt. And solve the circuit and obtain the voltage. And the voltage we obtain is 6 volts, but the actual voltage is 12 volts, 2 times. Right? So this means that our assumption should be 2 times 1 volts. So let's take a look at this. The general idea is scaling. Did I give you the lecture notes? In this lecture, this is one of our lectures. Okay, let's take a look at this circuit. So first, we assume that our Vout equals 1 volt. So once we have the Vout, we can obtain the current I2. So we can obtain I2, which is Vout over 2K, which is 0.5 milliampere. So we have this current. So we can calculate V1. This is V1. So V1 equals 4K times I2 plus the V2, which is 3 volts. And then we can calculate I1, which is V1 over 3 equals 1 milliampere. Then we calculate I0, which is I1 plus I2 equals 1.5 milliampere. And the VO should be this VE. So this VE should be 2K times IO plus V1 equals 6 volts. So we solve the circuit in the reverse direction. First, we assume the output voltage. And here we just assume that this is not a 12 volt. This is not unloaded in the reverse direction. We assume this is 1 volt. And by solving this direction, this circuit in the reverse direction, we get 6 volts for the input voltage. But the actual output voltage is 12 volts. It's 2 times the calculated input voltage. So this is 2 times. So the output should be also 2 times. So in our assumption is that we assume is 1 volt. Right. So but the actual output should be 2 times the assumption, 2 volts. That's how we solve this circuit using this scaling. Any questions? Yes. So this method is that we do not know the Vout, so we assume the Vout, and solve the circuit in the reverse direction. We calculate, we obtain a voltage for the voltage source, which is 6 volts. But the actual voltage is 12 volts, which is 2 times the calculated input voltage. So we know that the coefficient, the scaling coefficient is 2. The scaling coefficient is 2. So that in order to generate 12, in order to have 12 volts input voltage, so this Vout should be 2 times 1. So this is 2 volts. This scaling to solve the problem. It's easier. Yeah, I think this method is easier than calculate the equivalent resistance and do the voltage and calculation. And another example. So the previous example we used the scaling, and this example we use the additivity to analyze this circuit. The additivity is that, for example, a circuit like this, we can use node analysis for the circuit. the node and calculate the node voltage. So once we have all the node voltage, we can calculate the current. But now is that it has two voltage sources. We can use the additivity of the circuit. And this is also called a superposition. So that if we turn off one voltage source and obtain the circuit, the first circuit, and then we turn off the other voltage source, so we obtain another circuit. And this is called superposition because that, as I introduced, that this is a linear circuit, so that fx1 plus f plus 2 equals fx1 plus fx2, right? So the circuit, if we add the current, so for this circuit we have current I1 prime, and for this circuit we have I1 double prime. So if we add them together, we can get the total current for the original circuit. So this is the general idea of superposition. So let's take a look. So for I1, how to calculate I1? I think it's pretty straightforward, right? How to calculate I1. So these two resistors are in parallel, so we obtain the equivalent resistance. And in series with this, that is the 2K, and in series with the 3K, so 5K. So this is the current. And then for the other circuit, we need to calculate this I1 double prime. This is a little bit more complicated. So that the first, these two resistors are in parallel and then in series. Right? So we can calculate I2 first, I2 double prime first, and then use the current division to calculate the I1 prime. So we add I1 prime and the I1 double prime against the current I1 original circuit. So no problem on how to calculate I1 prime. How do you have any questions on how to calculate I1 prime? No problem. So I will introduce how to calculate I1 double prime. So this is a little bit more complicated. So in order to calculate I1 double prime, we need to calculate I2 double prime, and then use the current division to calculate I1 double prime. So the I2 double prime root 2. This is 6K plus 3K. So for the I2 double prime, these two resistors are parallel. So we can calculate this. And the 6K is in series with the equivalent resistance plus 6K. But the reference direction is the opposite of the reference direction. So it is opposite of the actual direction. So we have a negative sign here. So once we obtain I2 double prime, we use the current division, which is half. Yeah, half of the I2. So we can obtain I1. So we have superposed individual voltage source solutions. So in this method, it can be extended to the circuit that has more than two sources. This is voltage source, but it can also be current source. But we use each source work independent and turn off or shut down other sources and add the current or voltage together so we can get what we want for the original circuit. So in this one, we shut down this multi source. So we use a short circuit and and then we shut down this multi source and use a short circuit and the result of the true circuits together. Original circuit. The same also applies to the circuit with the current source. But to turn off the current source, we use open circuit. So that's the difference. So in any linear circuit containing multiple independent sources, the current or voltage at any point in the network may be calculated as the algebraic sum of the individual contributions of each source acting alone. But this only applies to current and voltage. This does not apply to power because the power is not linear. So for calculate power, so you use this superposition to calculate the voltage and the current for each circuit, and then add the voltage and the current together to get the voltage and current of the original circuit, and then calculate them. But in each the power on this one plus the power on this one does not equal the power on this one. So the power cannot be added. Only voltage and current. So let's have another example on the circuit that has the current source. So in this circuit, it has two sources, one voltage source and one current source. So the voltage source are replaced with a short circuit. The current source are replaced with an open circuit. So this circuit equals these two. The first one shut off the voltage source. So use short circuit. And this one we shut off the current source. So use our open circuit. And by solve these two simple. So this circuit is more complicated than these two, right? So these two only have one source. So we solve the VO prime and the VO double prime, and we add them together. That is VO. Let's do this as an example. So you maybe 5 minutes to do this example. The first one is simple, right? Use the current division. So the first one, the current is known, and it's one branch, the second branch. So use the current division, you can calculate I0. Use Ohm's law, VO prime. Yeah, see what's the value you get for VO prime. So did you get real prime? How much did you get for real prime?
Yeah.
No, this is the current position. I go to that. And you use so you calculate ideal is the current position.
Yeah.
Okay, let's take a look. Take a look. So the IO should be 2 milliampere, right? Times the current depletion is 1 plus 2. This should be no problem, right? The current division will obtain the IO. And then you so the VO prime equals the IO prime times the resistance. So this equals 4 volts. This is for the first circuit. This is for this circuit. Right? And then for this circuit, this is the 3 volts and how many 3 resistors. Use you can assume the current is I and calculate I and then calculate the voltage. No problem. How to solve this. So that the VO double prime equals 3 times the 6 1 2 and then the VO equals 1 plus double prime. So this equals 6 volts. That's pretty easy, right? Because this circuit is complicated. You need to have a lot of equations. So we simplify this into smaller, simpler steps and add without. And yeah, so this one, I think a simpler one on this will be understand. So you know how to solve this. So the superposition applies to the current and the voltage in a linear circuit. It cannot be used to determine the power because power is not a linear function. So the problem solving strategy. So in a network containing multiple independent sources, each sources can be applied independently with the remaining sources turned off. To turn off a voltage source, replace it with a short circuit. And to turn off a current source, replace it with an open circuit. When the individual sources are applied to a circuit, all the circuits lost at the same point. We assume that can be applied to a single solution. The results obtained by applying each source independently and then added together algebraically to it. This is the superposition. Okay, the next one is the source transformation. So equivalent circuit, we will always talk about the equivalent circuit. The circuit with VI characteristics are identical with the original circuit. So here, source transformation is the process of of replacing voltage source in series with a resistor by a current source in parallel with a resistor. So this voltage source in series with a resistor can be transformed to a current source in parallel with a resistor. And also we can this direction or this direction. Sometimes this can have simplified circuit. And the relationship between, for example, if we know the Vs and R, we want to convert this circuit into this one. The R is the same with the R, but what's the value for Ix? So that we use this equation. Is equals Vs over R. So we know Vs, we know R, we calculate Is and R here. So we convert this circuit to this circuit. And if we convert, if we know this circuit, if we know Is and R, we calculate the Vs using Is times R. So we calculate the Vs. So we can convert this circuit to this circuit. Just an example. Here. And also this also applies to a control source. And the terminal, so remember the terminal of the current source is directed toward the positive terminal of the voltage source. So if the voltage source is positive negative, so the current is up. If it is negative positive, the current is the direction of current is down. So let's use the source transformation to find the Vx. Then we will have one for the homework. So let's use the source transformation to find Vx. Which one is Vx? Not Vx, it should be Vo. It should be Vo. Use the source transformation to find Vo. Or V0, this V0 or V0. VO. Oops. Should be VO. So what we do is that first we transform this one, these two, the resistor parallel with the current source. Convert this one into a voltage source and a resistor. So this resistor is series with this resistor. And yes, and then we can so and yeah, and this one with the series with voltage source can be converted into a current source, which has a parallel. So let's take a look at this one. This current source together with the resistor, it can be converted into a voltage source because the direction of the current is down. So this is positive. And the resistance is 4. What's the voltage? The voltage is 4 times 3. Right. So And then we have the two ohm resistor here. We have the 8 ohm resistor here. And for this circuit, this is a 12-volt voltage source in series with the 3 ohm resistor. We can convert it into a 3 ohm resistor in parallel with the current source. And because the direction of the current source should go from negative to positive, so it is up. And the current is 12/3, which equals 4. So the above circuit is simplified into this circuit. We have further simplified this circuit because we can see that these 4 and 2 they are in series. So this becomes a 6 ohm resistor. Right? So this becomes a 6 ohm resistor. So this becomes a 6 ohm resistor, and we can use the source transform again. This is the voltage source in series with resistor. We can convert this one into the current source. So the current source is 2 ampere, and the 6 ohm, and then the remaining circuit keeps the same. Right. So this circuit is simplified into this circuit, and the current source can be combined with 2 ampere and 4 ampere can be combined, and use the current division. We can obtain the current on each resistor, and then once we obtain the current on each resistor, we can calculate the voltage on the 8 ohm resistor. So yeah, that's how we solve this problem. Any questions? That's the end of this lecture. For your homework, you will do 2 points. Yes, this homework, and also this one. You need to use your source transformation to calculate ideal. Similar to this one. Okay, that's the end of this lecture.